Right then, welcome back for another deep dive with us. Today, we're tackling something that sounds like it's straight out of science fiction,
Yeah.
but it's quickly becoming, well, just science. Quantum computing.
Mm-hmm.
Now, I know some of you might be thinking, here we go again, more jargon,
Right.
but that's not what we're about here.
Mm.
You're here because you want to know how this really complex field is actually showing up in the real world right now.
Yeah, absolutely.
We're ditching the theoretical debates and
Yeah.
focusing on real, concrete advancements that could actually impact your life sooner than you think.
Yeah, much sooner.
So, to get us started, would you like to introduce yourself?
Sure. I'm a researcher specializing in quantum algorithms and their practical applications.
Wonderful to have you here.
Thanks for having me.
Well, you know me, I just get very enthusiastic about these fascinating topics.
I can tell.
So, we've been digging through a ton of research, application reports, articles on the future of this tech, all to bring you the key takeaways. What's our mission for this deep dive?
Well, simply put, to demystify quantum computing. We'll look at concrete examples of how these incredibly powerful machines are being used, the problems they're solving, and why any of this should matter to you.
Exactly. And get ready for some surprises along the way.
Definitely some aha moments, I
Well,
think.
I hope so. So when you think quantum computing, you probably picture, I don't know, futuristic labs, scientists scribbling on whiteboards.
Yeah, the classic image.
But what's so fascinating is that this tech is already impacting areas that you might not expect. It's like we're going from sci-fi to, well, the supermarket.
Right. What's captivating is that we're seeing genuine, real-world applications emerge, and they're not just theoretical anymore.
Right, like right now.
Yeah, think about it. New medicines getting to you faster, maybe even cheaper groceries because of smarter supply chains, or even cleaner air because quantum computers help design better carbon capture materials.
It's almost a bit much to take in. It seems too good to be true.
It's definitely a lot.
What's driving this shift from theory to practice? What's changed?
Two main things, really. First, the quantum hardware itself has come a long way. Companies like IBM, D-Wave, they're running machines with over 100 qubits.
Wow, okay.
That's a huge leap forward, although we're still some way off from the really powerful, fault-tolerant machines of the future.
Right, so not quite there yet.
Not quite. The second thing is the development of hybrid algorithms. This combines the strengths of quantum and classical computers to solve really complex problems that are relevant today.
Okay, so it's not a complete quantum takeover.
No,
More like a partnership, a boost to our existing tech.
precisely.
Let's jump into some examples, starting with something that affects everyone. Healthcare. Specifically, drug discovery, which has always seemed like this massive, expensive, and slow process.
Oh, absolutely. Traditional drug discovery can take over a decade, cost billions of dollars to bring just one new drug to market.
It's mind-boggling.
A major roadblock is the sheer complexity of simulating how molecules interact at the quantum level.
Right, because everything's happening at that tiny scale.
Yeah, exactly. Even the most powerful supercomputers we have struggle with the sheer number of possibilities when you get down to the quantum mechanics of how molecules behave.
Okay, so this is where quantum computers come in. What's their advantage in this molecular world?
The advantage lies in the qubit, the building block of quantum computing. Unlike classical bits, which are either 0 or 1, qubits can be in a state of superposition.
Superposition.
It's like a classical bit is a light switch, on or off.
Ugh.
A qubit is more like a dimmer switch. It can be anywhere in between. This lets qubits represent many possibilities at once.
All at the same time.
Yes. So when you're simulating molecules, qubits can act like much more accurate models, mimicking the behavior of electrons and atoms as they interact.
That's pretty powerful. Could you give us a real-world example of this in action?
Certainly. A few years back, researchers used Google's Sycamore quantum processor to simulate a protein interaction involved in COVID-19. This simulation, which could have taken decades on a classical supercomputer, was done in days on the quantum system. Days. And it's not just about speed, it's about understanding how viruses work in ways that could lead to completely new antiviral therapies.
Decades to days. That's incredible.
It really is. It's like trying to crack a combination lock.
Okay.
A classical computer tries each combination one by one. A quantum computer can explore all combinations at once, basically.
I see.
That's the kind of speed up we're talking about when simulating those complex molecular interactions. And for someone waiting for a new treatment, maybe a better migraine drug, this could be life-changing.
Absolutely. It makes you think about all the possibilities.
Definitely.
Okay, so quantum computers could unlock new medicines much faster.
Yeah.
That's a huge implication.
It is.
Let's move to something a bit more everyday. Traffic.
Okay.
I think we've all been stuck in traffic, feeling frustrated.
Oh, yeah.
Our research suggests that quantum computing could actually help with this.
It's true. Optimizing logistics, whether it's planning delivery routes, airline schedules, or even city traffic, involves dealing with a huge number of possible solutions. It's huge.
And as the number of variables grows, finding the best solution becomes too much for even the most powerful classical computers.
So it's another case of the problem being too big, too complex.
Exactly. And this is where quantum annealing comes in.
Okay, what's that?
Imagine it like this. A quantum computer can find the lowest energy state of a system. In practice, this often translates to the best solution for a difficult optimization problem.
Interesting. And there's a real-world example of this, right? Something about buses in Lisbon.
Yes, Volkswagen worked with D-Wave, a company specializing in quantum annealing, to optimize bus routes in Lisbon.
I see.
They used a quantum annealer to analyze all the possible route combinations, and the results were impressive.
Like how impressive?
They saw a 15% reduction in traffic and a 20% decrease in fuel consumption for the buses.
Wow, that's a significant difference.
Think about it. Less time wasted in traffic, lower emissions, a more productive workforce.
It's amazing how something so complex can have such a tangible impact. It really is. And if these optimizations can be scaled up to bigger transportation networks, the impact could be huge.
So from traffic, let's move to a global issue. Climate change. Our sources suggest that quantum computing could be a powerful tool here.
Absolutely. One of the biggest challenges in fighting climate change is finding new materials that can capture carbon dioxide from the atmosphere or make renewable energy more efficient.
Okay, yeah.
But designing these materials requires understanding how atoms interact at the quantum level. And as we've talked about, simulating these interactions for complex molecules is very difficult for classical computers.
It's that simulation bottleneck again.
Exactly. In 2023, IBM researchers used a 127-qubit quantum computer to model a molecule designed to capture QAs.
Oh, wow.
This simulation, which might have taken months or even years on a classical computer, was done in just hours on the quantum system.
That's another huge time saving.
It really is. This means we can discover and develop new carbon capture technologies much faster. Quantum computing might not just offer a faster solution, it might be essential for reaching our climate goals.
It's like it's becoming a necessity.
In some ways, yes.
And it's not just carbon capture, right? There are other climate-related applications too.
Right. Quantum computers can also be used to optimize things like the layout of wind farms to maximize energy production.
Makes sense. You need to account for all those variables.
Exactly. You need to consider wind patterns, the landscape, even ecological factors. Quantum algorithms can help design more efficient and productive renewable energy systems.
It really changes how you think about quantum computing. It's not just a futuristic tech, it's a tool for tackling one of the biggest challenges we face.
I agree.
Now, let's move to the world of finance. It's an industry known for its complex models and massive amounts of data. How is quantum computing playing a role here?
Financial markets are incredibly complex, influenced by everything from economic indicators to geopolitics to social media trends.
It's a lot to keep track of.
Predicting market behavior and managing risk requires analyzing huge data sets and running complex simulations.
And this is where quantum computing can help.
Precisely. Its strengths in handling large data sets and solving optimization problems make it a potentially game-changing tool in finance.
Can you give us some specific examples of how it's being used?
One area is portfolio optimization. Companies like JPMorgan are using quantum algorithms to analyze a much wider range of investment possibilities than classical computers can handle.
So, finding the best way to invest money.
Yes, finding the optimal balance between risk and reward. Another application is fraud detection. Quantum algorithms can spot subtle patterns in transaction data much faster, leading to better fraud prevention systems.
So it's like a security boost.
In a way, yes. It's about staying ahead of the curve in a very competitive and data-driven industry.
Now let's talk about artificial intelligence. AI is already changing so much in our lives.
Yeah.
One of our sources even called the combination of AI and quantum computing AI on steroids.
It's a bit of a dramatic term.
It is a bit out there.
But it does hint at the potential synergy between the two. Training large AI models, the kind used for things like language processing or image recognition, requires a lot of computing power and energy.
Yeah, AI is energy intensive.
Quantum computing could speed up certain parts of the machine learning process.
And how would it do that?
One way is through quantum neural networks. These are neural networks that use quantum mechanics to learn complex patterns from data more efficiently.
Right.
This could mean faster training times for AI models and more energy-efficient AI systems.
So more efficient AI, that's pretty interesting.
It is. And we have another example from Google, this time in healthcare.
Okay, what did they do?
Google's quantum AI team used quantum machine learning to improve the accuracy of medical diagnoses.
Interesting.
In one study, they trained a quantum-enhanced model to diagnose heart disease with better accuracy than traditional methods.
So better diagnoses.
Yes, think of it this way. Classical AI is like a chef following a recipe step by step. Quantum-enhanced AI is like a chef who can taste a dish once and know exactly how to make it perfect.
That's a great analogy. It really helps to understand the difference.
For that, it helps.
Now, we can't talk about the future of computing without talking about cybersecurity. Our current encryption methods might be vulnerable to future quantum computers.
That's a big concern. Most of our online security relies on the fact that classical computers struggle to solve certain math problems, like factoring large numbers.
Right, it's like a code that's hard to crack.
Exactly. But there's a quantum algorithm called Shor's algorithm that can factor these large numbers much faster.
So a quantum computer could break our current encryption.
A powerful enough one, theoretically, yes. It could render our current security measures obsolete.
That's worrying. What's being done to address this?
Well, the same advancements in quantum computing are driving innovation in cryptography. We're seeing the development of quantum cryptography, which aims to create truly unbreakable codes using quantum mechanics.
Unbreakable codes. That sounds promising.
One key technology is quantum key distribution, or QKD.
Okay, what is that?
It uses photons, particles of light, to transmit encryption keys.
Oh,
Any attempt to intercept these keys would disturb the photons, alerting the legitimate users to the intrusion. It's like a self-destructing message.
I see. So if someone tries to eavesdrop, you'll know.
Exactly. And it's not just theory. We're seeing QKD being tested and used in real-world settings, especially in areas like government communications and finance.
It sounds like we're moving towards a more secure future, even with the threat of quantum computers.
Yeah, it's the goal.
We talked about quantum optimization in logistics and traffic management. Are there other applications of this optimization power?
Definitely. The ability to find the absolute best solution from a huge set of possibilities has applications in many industries.
Like what?
Think about optimizing airline schedules to minimize delays or fine-tuning production processes in factories to reduce waste.
Okay, yeah, that makes sense.
Algorithms like QAOA and quantum annealing are being used to solve these complex problems much faster than classical methods.
And we have real-world examples showing this works.
Exactly. The Volkswagen project in Lisbon is a great illustration of that.
So it's all about finding the best solution, the most efficient way to do things.
Precisely.
We've talked about drug discovery, but what about other applications in healthcare and personalized medicine?
Beyond finding new drugs, quantum computers can help us understand complex biological systems better.
Ah,
This could lead to advances in research on diseases like Alzheimer's and Parkinson's.
that would be huge.
It would. And the ability to analyze large amounts of genomic data could lead to personalized medicine, where treatments are tailored to your specific genes and lifestyle.
So healthcare, that's specifically for you.
Exactly. It's about identifying disease markers and predicting how different treatments would affect you individually.
That sounds like the future of healthcare.
It's definitely a promising area.
Looking even further ahead, what are some other areas where quantum computing could have a big impact?
There are so many possibilities. We might see the development of a global quantum internet, which would be incredibly fast and secure.
Wow, a quantum internet.
In material science, we could discover new materials with amazing properties, like superconductivity at room temperature.
That would revolutionize so many things.
It would. And in space exploration, quantum computers could help optimize spacecraft trajectories or simulate things like black holes in more detail.
It's mind-blowing to think about.
It really is. But it's important to remember that quantum computing is still a young field.
Right, there's still challenges
Exactly. We need to build larger, more stable quantum computers.
with more qubits.
Yes. And we need to develop better ways to correct errors in quantum computations. Plus, we need to figure out how to integrate quantum computers with our existing classical systems seamlessly.
It sounds like a lot of work still to be done.
It is. It's a bit like the early days of classical computing. Lots of potential, but a long way to go.
So to wrap up, what's the main takeaway for our listeners about real-world quantum computing?
I'd say the key message is this. Quantum computing is moving from theory to practice. We're seeing real-world applications in many areas, from drug discovery to logistics to climate change.
And it's not just hype. We've seen concrete examples of how it's being used.
Absolutely. And while there are still challenges, the potential is huge.
So we've gone from those faster drug discoveries and optimized bus routes to the modeling of carbon capture materials. It's clear that the journey to harnessing this technology has really begun.
It has. And you, our listener, now have a better understanding of how quantum computing is being applied beyond the hype.
Exactly. So for our final thought, I'd like you to consider which of these applications you think will have the biggest impact on your life and on society. Will it be revolutionary new medicines, better infrastructure, solutions to climate change, or unhackable communication?
It's an exciting time.
It really is. I encourage you to explore these areas further. There's so much information out there. This is an ongoing story, and the next chapter is going to be fascinating.
I completely agree. The field is evolving so quickly, and the applications we've discussed are just the beginning.
Thanks for joining us on this deep dive. Until next time, keep that curiosity burning.